Hi there, so this is my review of lecture 26 about complex matrices and FFT. This video will talk about the chapter 9.1 about complex number, so sort of our review of complex numbers, and let's dive into it right away. First I will begin with the complex plane. So as you can see, we begin with this how to express the complex number as z equals to a times ib. So it is pretty similar to what we have earlier on the real number. So let's say on the real one we have the x and y in case of two dimension, but in the complex one we have this kind of thing, so the real and the imaginary part. So here the a is belongs to the value in the real part, and the ib, the one with the I in it, is belong to the one in imaginary part. Okay, so for example, a quick example will be like 1 plus 1 I. Okay, so that will be 1 unit of real and then 1 unit of imaginary. And then there's an idea of complex conjugate, which is just switching the sign of the imaginary part to the negative if it were positive, or the other way around. So in this case, the complex of z, here we have, is 1 minus 1i. Okay, and notice that how I use this notation, like the bar on top of g, to denote the conjugate of z. Okay, and then there are two important facts here, that if you add the complex number and its conjugate, it will be real, and then if you multiply them, it will be real also. This is a useful fact. So for example, here if I add z plus z bar, then I have 1 plus I plus 1 minus I, then of course I have 2, and the same thing if I multiply them, then I have 1 plus I. Let's just do it the classic way, right? Okay, so you have 1 and minus I plus I, and then minus I squared, and then this will be cancelled, and then minus I squared is 1, so you have in this case 2 again, right? Because I squared is minus 1. Okay, so that's about the complex plane. We finished this already, and then we move on to the polar form. Okay, let me delete this one. So the polar form is another way to express a complex number. So it has another form, as you already see here. So the z, so this form is also equal to the r e to the power of theta I, and this will, the theta, this part actually equal to cos theta plus I sine theta. So this is called the Euler's form. So there's this Euler's form, which is just this part right here. Okay, but then you have like this part right here. This part right here is the polar form, and I believe this part right here, the one that we started with, a plus ib, this is called the rectangular form. Rectangular form. Okay, so just keep in mind that you have the polar form, which is r times e to the power of theta I, and then the e to the power theta I is the Euler's form, which equals to this value, cos plus I sine, and then yeah, we begin with the rectangular form. Okay, and another idea here is that the idea of the absolute value, or the modulus, which is exactly like the magnitude of what we have in the vector. So you just have to square the real component and the imaginary component in this case. So the length squared, we call it the z squared, is just the a squared plus b squared. So in the case of this matrix we have like if z is like 1 plus I, then this is just 1 plus 1, and this is z squared, and the z and the magnitude or the absolute value or the modulus is the square 2, and this is also what we call r here. Okay, so r is what goes here in the polar form, as you can see here. So let me write that again. The polar form z is r I e to the power r e to the power of theta I. Okay, and let's continue this example. You have the r already, so you have r equal 1, sorry, square root of 2, but how do you get the theta? And here it's pretty simple, because if you imagine that you have I to the imaginary axis, like this one. So imagine that we want to now plot the z equal 1 plus I. Okay, so you have the I to the imaginary axis, and you have the 1 to the real part, and this will bring you to this vector, right? And this is, if you imagine that there's this degree right here that goes from 0 into the 2 pi. So this is and this is pi, okay, pi equals to 180 degree, and this is a quarter of pi, right? Because this is a half of pi. So this is quarter of pi, so we know the degree is 45 degree. Or another way to find it is also by using the tan inverse, I believe. I kind of forget what it's called, but the tan inverse of this side divided by this side. Oh, this side divided by this side. So tan inverse of 1 over 1, and this should be also, we know the degree from this formula, so we know it is equal to 45, and that's what we have here. So we can now expand the polar form to the r times cos theta plus I sine theta, which is 1 here, cos of 55. Okay, and now notice that r is actually that circle, the radius of the circle. So in this case, this complex number here, it's going around the unit circle here. Okay, a unit circle of radius of 1. Okay, so that's about the polar form. We finished this one. And then there's an idea also of the powers and the products of z. Okay, now it is mentioned that computing the powers are really easy in the polar form. So let's go back to our example here. Let me delete some of these. So we have again z to 1 plus I, really simple, and you want to find what is the z squared in this case. And it is easy in the polar form, so let's use that. So remember that z is equal to the r exponential of theta I, and then so if you have like square of them, then you can just do this. Also you square this one, and this will be like r squared e to the power of 2 theta I right now. So what you're doing is just you're just squaring or nth powering whatever the r is, and then you just double the degree. So in this case you will have r equal 1 again, because we have 1 here. Initially we have 1, right? And then I'm sorry, no, my mistake. We have the r is square root of 2, right? So I have now r2, and also the degree, we used to have this, the pi, quarter of pi. Now we have just double them, so half of pi. And I am sorry, so the first example, the z should be have the r of square root of 2 instead of 1, and it should not be the unit circle. I'm really sorry about that, but I hope you got the idea. So please also keep in mind about this formula when you want to compute the powers of z. And that's actually the summary of chapter 9.1. Thank you.